Hello and welcome to the NPTEL MOOCs course on Foundation for Virtual and Augmented Reality Systems. We are going to continue our discussion on visual perception and displays. So, in the previous part of the lecture, we talked about physiology of vision and how we visually perceive, how the light comes to our eyes, what happens with that light and how it is carried to the brain. In this lecture, we are going to continue our discussion. We are going to learn about how this knowledge that we have acquired in the previous part of the lecture, how they are going to help us understand the working of head mounted displays and other kind of displays that we typically associate with immersive experience. So, let us try to put whatever we have learned so far, put everything together and try to understand how the headsets work. That is the most prevalent and easily associated form of displays that we think of while thinking of immersive experience. So, when we talk of human eyes, then whatever we have gathered so far, based on that, what we can say is that an eye looks something like this as shown in this figure. So, it shows a cross section of the human eye facing the left direction. Now, the light rays are falling on it, they can assume to be, we can assume them to be parallel light rays entering from the left side. Then we have cornea, which in itself can be considered to be a powerful lens, but having a fixed focal depth. We have lens, human lens, natural lens, variable focal depth, and the retina, the image surface or the portion of the eye where the light rays fall and then gets transmitted to the brain through optical nerves. Now, this is the, we can call it the image surface, which is a non-planar surface, as you can see from the diagram. Now, that is the natural human eye. Now, let us consider an engineered lens setup. So, this is the engineered lens, that is artificially created lens, parallel lights coming from the left side, they are converging to a focal point which is on the focal plane, and the distance between the lens and the focal point is the focal depth. Try to understand this concept with respect to the natural human eye shown here. So, what are the differences between the natural human eye and the engineered lens setup? There can be few differences that we can highlight. One is focal plane is replaced by retina. When we are transmitting from, when we are comparing the human eye with an engineered lens, we can say that the focal plane is replaced by retina. So, in case of a human eye, there is no focal plane as such, but there is a non-planar retina which replaces the concept of focal plane. That is a spherically curved surface. Now, retina contains photoreceptors that convert light into neural pulses. Similar thing is not there in an engineered lens. The interior of the eyeball is actually liquid as opposed to air through which light passes in the case of an engineered lens. So, in case of an engineered lens, light falls on the lens and then passes through air to reach the focal plane, whereas in case of human eye, there is no air inside the eye, rather a liquid through which the light passes after getting transmitted through the lens. a ray of light travels through 5 media before hitting the retina in the case of human eye. Now, the idea is illustrated here. We have first air through which the light comes, then cornea, then one liquid, then lens, then another liquid. So, 5 different media, and each is having their own refractive indices, that means the amount of light that passes through, which determines the amount of light that passes through the medium. Air 1.009, that is the refractive index, then cornea 1.376 refractive index, aqueous fluid, this part, a liquid type material 1.336, natural lens N4 1.413, and finally another liquid vitreous fluid 1.337. So, light passes through all these 5 media with different refractive indices before it reaches the retina, which is not the case with artificial or engineered lens setup. So, if we try to understand the normal eye operation, let us see what happens. So, outer diameter of the eyeball is approximately 24 millimeter, implies that a lens of at least 40 diopter, 40D diopter required to cause convergence of parallel rays onto the retina center. So, light is coming in this way, and to converge it to the retina center, that is the focal point, we can roughly call it the focal point, we require a lens of at least 40 diopter if we are thinking of a single lens. But in case of our eyes, there are effectively 2 convex lenses, cornea and the lens. So, both cornea can be considered as a lens, as a type of lens, and lens is of course a lens. Then we have to combine their diopters to see whether it matches the required 40D power of the lens. So, cornea optical power is 40D, approximately 40 diopter, and eye lens is less powerful, approximately 20 diopter, that is well known. So, when we combine these 2 lenses, then their combined power of cornea and natural lens is 60 diopter, which is more than what we require when we are talking of a normal eye. So, since the combined power of the system is more than 40 diopter, images of far away objects are therefore focused onto the retina because of this combination, cornea and lens. So, generally with normal eye there is no issue with that. Now, what happens with a VR headset? Suppose we are constructing a VR headset by placing a screen very close to the eyes. Now, what we want? We want to bring it close so that it fields view of the user. User is not able to see anything beyond the screen. The optical power is increased by using a convex lens functioning in the same way as reading glasses. So, inside the VR headset there will be a convex lens plus a screen that will render the image, and the lens will help us focus it to the retina. So, this is the VR headset engineered lens setup, where we have the screen, we have the engineered lens, and the light from the screen passes through the engineered lens, then falls on our eye, and then normal eye operation takes over. And the distance between the screen and the engineered lens should be the focal distance of the lens, engineered lens, then to get the best experience. So, to get the best experience, the lens, engineered lens, that is part of the VR headset, is usually placed at the distance of its focal depth. The screen appears as an enormous virtual image that is infinitely far away. If we follow first condition, then the second condition will be followed. It may be noted, however, that a real image is nevertheless projected onto the retina. We do not perceive world around us unless real images are formed on our retina. So, here our objective is to make the artificial system comprising of the screen and the engineered lens, that is part of the headset or any other display, work in a way such that they convert the light into normal light that falls on the eye, so that eventually we get to perceive the image whatever we are seeing after it falls, the light rays falls on our retina. So, essentially we are supplementing our normal eye operation with a special setup that utilizes the normal eye operation. So, then how do we perceive the depth or three-dimensional properties of objects? How do we do that? One important concept here is the field of view, that is the region visible to human eye. It is an angular measure of what can be seen at a single point in time. So, if this is the eye, this entire frustum, view frustum, refers to the field of view. So, this human eye has approximately 180 degree horizontal field of view as shown here. So, if these are the lens eyes, then we have 180 degree field of view horizontally, and vertically we have 150 degree field of view. So, within this range we can see things, and horizontally within 180 degree we can see things, utilizing both our central and peripheral vision. So, horizontal FOV is 180 degree, vertical FOV is 150 degree. Now, when we are looking at something using both our eyes, both the eyes can see the same area over an angle of about 120 degree when focusing on infinity. So, this 120 degree region denoted by this region is a common region where both the eyes get to see things same thing. Otherwise, outside this region, this part is seen only by the left eye, this part is seen only by the right eye. So, this is called binocular vision. This common area, 120 degree area, both the eyes are used to see the same image within this region. Outside this region, some part is seen only by the left eye, whereas some other part is seen only by the right eye. Now, this binocular vision enhances depth perception and relationship between objects in 3D space. So, it helps us understand the relationship between objects in 3D space as well as enhances our depth perception. This brings us to the related concept of stereoscopy. So, we use two eyes to view two images simultaneously, some part of which may be overlapping due to the common region in our field of view. The left eye processes the left image, right eye processes the right image. So, this is the left eye, this is the right eye, left eye suppose sees this one, right eye sees this one. There is a common part which both the eyes sees and some part which only one eye sees. So, in this context maybe this part is seen only by the right eye, whereas this part is seen only by the left eye. Now, these two 2D images each for one eye, when they gets processed simultaneously, that processing generates a 3D view of the objects. So, stereoscopic vision essentially helps us perceive 3D view of the object, which is aided by our binocular vision property. That is about perceiving 3D. Now, let us try to understand how we perceive motion or perception of movement. So, a virtual world may allow up to two types of movements in 3D space: translational, which is used for navigating in the 3D space, and rotational, which is primarily used for moving at different angles along the translational axis. So, broadly these two type of motions can be there in any virtual world, and how can we perceive them? Now, there is this concept of degrees of freedom, which is an indication of the different ways an object can move in space. So, there can be total 6 degrees of freedom in 3D space. There are 3 rotational degrees of freedom, which are called yaw, roll and pitch, and translational 3 degrees of freedom along x, y and z axis. So, in this small animation you can see the yaw, roll and pitch things. This is the roll part, this is the pitch part. So, this is the roll part, the pitch part, and this is the yaw part. Then we also have the translational degrees of freedom, 3 degrees of freedom along the 3 axes, maybe x, y and z axis. So, we perceive motion with respect to the degrees of freedom, whatever is supported. Now, what are the issues here? What this knowledge that we have acquired so far tells us. So, basic physiological properties such as photoreceptor density can directly impact engineering requirements for visual display hardware. So, the way we design the hardware can be determined based on kind of photoreceptor density. So, the displays are generally designed based on that knowledge. Engineered systems must be good enough to adequately fool our senses. So, our brain perceives in a way that has been learned over generations. When we are trying to perceive things differently, that engineered system must be good enough to fool our natural way of perception, but need not have levels of quality beyond the limits of our receptors. So, we should know how much our brain, our system, our body can process and how much it cannot. So, accordingly we should design the system. VR display should ideally be designed to perfectly match the performance of the sense it is trying to fool, in this case the visual sense. So, in order to achieve that, what are the important considerations? Spatial resolution, that is how many pixels per square area are needed, is one consideration. Then intensity resolution and range, how many intensity values can be produced and what are the minimum and maximum intensity values, on the basis of our knowledge about how many such values can be processed without compromising our perceptual quality. And thirdly, temporal resolution, that is how fast do displays need to change their pixels. In other words, frame rates or refreshing. Frame rates are very important, particularly in the context of motion perception. We need to understand how objects are moving. So, which frame rates allow us to perceive motion smoothly without any jitter. Let us try to understand spatial resolution, what studies tell us and how it can be useful. So, we see individual lights when a display is highly magnified. As it is zoomed out, we may still perceive a sharp diagonal line as being jagged, known as aliasing. Say for example, here the more we zoom out, the more we get to see this type of aliasing effects. Instead of smooth lines, we get to see some staircases, jagged lines, that is called aliasing. Everywhere we can see that. Similarly, there can be other effects. One important effect is called screen door effect. It is commonly noticed in images produced by LCD projector. As you can see here, it appears as if there is a screen on top of the image because of this zooming thing. So, the question is, what kind of resolution we should support so that these type of effects are not visible even if we are zooming out even if we are zooming in or zooming out the image. So, what does the display pixel density need to be so that we do not perceive individual pixels or these aliasing effects? Now, there is a concept called retina display. In 2010, Steve Jobs, probably all of you have heard of him, of Apple, claimed that 326 pixels per linear inch or PPI is enough achieving what they called a retina display. So, retina display is a kind of display where the resolution supported is minimum 326 PPI or pixels per inch. But that is found to be suitable when the display is at a distance, for example, TV, laptop, smartphone, etc. Now, since we typically experience AR using displays that are at a distance from our eye, then this type of retina display concept can be a good idea to take into account in design when we are dealing with AR experiences. But in AR experiences also, if we are talking of experiencing AR through head mounted displays or something which is very close to the eye, then probably this retina display in its traditional form is not very suitable. In case of VR headsets also, which is very close to the eye, user is not looking at the screen from a reasonably large distance. So, by inserting a lens for magnification, the display brought very close to the eye, and in that case what happens is that implies that PPI requirement is much higher, probably 7 to 8 times higher than what is there in a retina display. So, for VR headsets or any wearable display which is closer to the eye, to get the immersive experience, we need to have resolution which is much higher than retinal display resolution, 7 to 8 times higher maybe. Also, we require corrective mechanisms to avoid aliasing or screen door effect for VR headsets in particular. Now, that can be done through several means. For example, adjusting the field of view of the headsets, then foveated rendering techniques. These are different ways to render content on the screen, and so on. So, different strategies can be adopted to reduce the effect of aliasing or screen door effect or jaggedness, along with increasing the resolution. That is about spatial resolution. Then there is another concern, that is temporal resolution. Now, in temporal resolution we require higher frame rates, much higher in comparison to ordinary television or movie standards of 24 fps or even 60 fps when trying to perceive motion in an immersive environment. The higher the better for VR headsets. So, if we are trying to design a VR headset where we will be experiencing virtual world where motion is involved, then it is preferable to have much higher frame rates as compared to typically what we get to see on our desktop or laptops or televisions. So, that is in a nutshell how the knowledge can help us design better displays, better headsets, what are the concerns, what we should keep in mind while designing such devices. So, let us summarize what we have learned. So, in this lecture we have covered few important concepts. First of all, how our eyes are made, what is the physiology of human vision, and how to understand how we perceive color, how we perceive depth, how we perceive scene. So, how the physiology affect our perception, and finally, we also touched upon how this knowledge can help understand workings of primarily headsets, but it can be relevant for other types of displays as well, as we have mentioned while discussing the concepts, in particular in terms of managing resolutions, frame rates, etc. So, this is about visual perception and its relation to design of XR systems, XR experiences. So, in our next lecture we will be covering auditory systems and how they are relevant for building better XR experience as well as systems. Most of the content of this lecture has been taken from this reference. If you can go through it, you will get more details. It will be very useful for further information. I hope you could follow the concepts and you could understand how our perception, visual perception works and how it relates to design of extended reality systems, including design of experience. So, looking forward to meet you in the next lecture. Till then, thank you and goodbye, happy learning.